everyone to another webinar hosted by Sembla. Today we are happy to have Fernando Parro. Fernando is an assistant professor of international economics at the Johns Hopkins School of Advanced International Studies. He has been previously an economist at the Federal Reserve Board in Washington, D.C. His research focuses on the trade and welfare effects of international trade policy, on the distributional effects of globalization, and on the dynamic labor market effects of changes in trade and migration policies. His research has been published in various journals, including the Review of Economic Studies and the American Economic Journal Macroeconomics. He holds a PhD from the University of Chicago, and today he is going to be giving us a talk on trade and labor market dynamics. So thank you, Fernando, and the floor is yours. As always, feel free to ask questions and to type them in the chat box, and Fernando will address your questions at the time he receives them. Thank you.
Okay, thank you, Francisco, for the invitation to present in this webinar. So this is on trade and labor market dynamics, and is a joint work with Lorenzo Caliendo and Max Borking. So Max works at the Federal Reserve Bank of St. Louis, and therefore the usual disclaimer applies. So this paper is part of a research agenda where we want to study the disaggregate effects of trade shocks. And specifically, understanding and quantifying the employment effects of trade shocks has been a central issue in recent economic research. And in this context, recent reduced form studies have provided substantial, robust evidence on the differential impact of trade shocks across local labor markets. And maybe the most prominent paper on this is the paper by Otterdon and Hanson that finds substantial differential impact of China's trade expansion on the US labor markets. However, reduced form studies say little about aggregate employment effects, about welfare effects, and they cannot really be used to study counterfactual policies. And that is the starting point of this paper. So what we do in this paper is to develop a general equilibrium model to study and to understand the disaggregate effects of trade shocks. And we apply our model to quantify the general equilibrium effects of China's trade expansion across US labor markets. And when thinking about how trade shock, say an increase in import competition from China, impact US labor markets, we are going to take into account several mechanisms. So for instance, different sectors and different regions in the United States have a differential exposure to foreign trade. So just to give you an example, a non-tradable sector is not going to be directly exposed to China, but some manufacturing sectors can have a high exposure to China. Second, even when a sector of or a region is not directly exposed to foreign trade, firms purchase intermediate goods from other industries and other locations that can be exposed to foreign trade. And therefore, through these indirect linkages, not only international trade, but also internal trade and sectoral trade shape the effects of an increase in import competition on US labor markets. But moreover, real wages are going to change across sectors, across industries, and across regions, and people are going to relocate across sectors and regions. But relocation is costly and it's a process that takes time. So for instance, switching industries could be relatively easy, but moving, let's say, from Alaska to New York is more costly and takes time because people have to gather a lot of information on economic conditions. And therefore, the labor market dynamics, the relocation process, more generally migration, also are going to matter. So therefore, understanding and quantifying the disaggregate effects of trade shocks requires taking into account all these channels I have mentioned. And in the first part of the paper, what we do is to develop a model of trade and labor market dynamics that is going to explicitly recognize the role of labor mobility frictions, good mobility frictions, input-output linkages, geographic factors, and international trade in shaping the disaggregate effects of trade shocks. In the second part of the paper, what we do is to show how to take a model like this to the data and how to use the model to perform a counterfactual analysis. And in particular, a model with all the characteristics, all the features that I just described may seem unfeasible to compute because in the environment I just described, agent decisions are going to depend on a large number of unobservable fundamentals of the economy that are usually hard to identify, such as bilateral migration frictions, bilateral trade costs, productivity levels by industry, regions, and country, and so on. So our methodological contribution in this paper is to propose a method, is to propose a way to solve this model and to compute the counterfactual analysis. And I'm going to explain this method in details later on, but what we show is that by expressing the equilibrium conditions of the model in relative time differences, we can solve the model and perform large-scale counterfactual without having to estimate the levels of these unobservable fundamentals of the economy. And in the third part of the paper, we apply our solution method to study how China's import competition impacts US labor market. And to do so, we are going to calibrate the model to 38 countries, 50 US states, and 22 sectors. And therefore, we are going to compute the employment and welfare effects across more than 1,000 labor markets. So during the presentation, I'm going to discuss several results that we have in the paper, but here let me highlight a couple of them. So we find that the increase in import competition from China led to 800,000 manufacturing job loss, which is equivalent to about 25% of the observed decline in manufacturing employment in the United States over the period 2000 and 2007. But we also find that the services sector expanded and that workers reallocate from a manufacturing sector to the services sector. Crucially, with this general equilibrium model, we can speak about welfare, and we find that aggregate welfare gains. So as a whole, the United States is better off, but welfare effects are very heterogeneous across labor markets. Still, we find that there are winners and losers. And we also find that the transition costs are important. So the adjustment process of the relocation of people across space and across industry, it takes time. But I'm going to discuss later on in more detail these results, and I'm also going to show you other results. So the plan for the rest of the talk is, first I'm going to go over the model. So the model has two main building blocks. First, I'm going to describe the household dynamic problem. Then I'm going to describe the production structure. And finally, I'm going to show you how we define the equilibrium of the model. So after doing so, I'm going to go over the solution method I just mentioned, how it works, and under which conditions this solution method is going to work. And then I'm going to go over the application to quantify the effects of China trade shock on US labor markets, and over the results. And finally, I'm going to conclude. So, as I said, I'm going to start by describing the household problem in our model. So in the model, there are going to be n locations that we are going to index by n and I. And each location has j sectors that we index by j and k. And in this model, a labor market is going to be a combination of a location, a region, and a sector. So think about what are examples of labor markets in this model: computers and electronics in California, or textiles in Wisconsin, or finance in New York. That is going to be a labor market in our model. So the first equation you can see here shows shows the value of a household. The value of a household in industry J and location N at time T. So a household that is working in labor markets NJ at time T receives a competitive nominal wage W that is going to depend on the labor market that you're working, on the industry and the region that you're working. And this household use her income to consume a basket of goods where PN is the ideal price index. So notice that in this model, we are going to have a sort of within region consumption inequality, because, for instance, Francisco and I, we can be living in the same state, let's say in DC, so we are going to consume the same basket of goods. But if Francisco is working in the finance industry and I am working in the textiles industry, we are going to earn different nominal wages, and therefore we are going to have different consumption power. A household that is non-employed is going to obtain consumption from home production, which is going to be given by this parameter Bn, which is going to be exogenous in our model. And then this household tomorrow decides, today decides whether to stay in the same labor market or to move to a different labor market tomorrow. And specifically, she's going to move, she's going to work, she's going to go to the labor market that delivers the higher expected value, subject to mobility costs, tau, and subject to idiosyncratic preferences, epsilon. I'm going to talk about this now. So tau NJIK is the migration cost from industry J and location N to industry I to industry K and location I and region I. So it's going to depend on the origin labor market and the destination labor market, and it's assumed to be additive and time invariant. And this mobility cost is going to be the same for all workers or all households that are located in the same labor market. And then epsilon is going to be an idiosyncratic preference that following recent labor market dynamic literature is assumed to be IID realization from a type 1 extreme value distribution with a dispersion parameter equal to nu. And this nu is going to be, as we are going to see in the next slide, is going to be related to, it's going to be a sort of a migration cost elasticity, and it's going to be a parameter to be identified. And finally, beta is the discount factor. Yes, so all workers have the same skill. Yes, so here in this paper, we don't distinguish across different skills. So we have more recent papers where we apply this same machinery to study the effects of the EU enlargement, where migration policies were eliminated. And in that paper, we allow for a different type of skills. But in these papers, there's gonna be only a single skill. So using the properties of the type 1 extreme value distribution, we can solve for the expected value of a worker in the labor market Nj at time t. And the expected value of, if you want a representative household in labor market Nj at time t is going to have two components. Current consumption and then this is a second term, and you can show that this second term is associated to the option value of migration. So as is common in the labor market dynamics literature, workers are not necessarily going to move to arbitrage wage differentials. So it could be convenient for them sometimes to wait even when there is a decline in real wages in a given labor market, because the option of waiting has a value for the workers. So the value of a worker is going to have two components: current consumption and the option value of migration. But more importantly, we can solve for the fraction of workers that reallocates across labor markets. So mu Nj IKT is the fraction of workers that move from industry J and region N to industry K and region I at time t. And it's going to depend on the expected value of going to the destination markets net of a mobility cost relative to the expected value of going to any other market relative to mobility cost. So for those of you who are familiar with the trade literature, so this equation that describes migration flows resemble to a gravity trade equation that describes the flow of goods across location. But this equation describes, this mu describes the flow of workers across different locations, where the numerator is kind of a bilateral resistant term, and the denominator could be interpreted as a multilateral resistant term in the context of gravity trade models. And you can see here that 1 over nu is sort of the reaction of migration flows to changes in migration cost, and in that sense can be interpreted as a migration cost elasticity, which is a parameter to be identified as is, and it is going to be analogous to what is a trade cost elasticity in the context of gravity trade models. With the migration flows at time t and with the distribution of employment at time t across labor markets, the distribution of employment across labor market is determined at time t+1. So the last equation shows the law of motion of employment across different labor markets at each time t. So from the system of these three equations, given real wages, the supply of workers across all labor markets is going to be determined at each time t. So what I'm going to do next is to show you, to set up the production structure of the model so that we can find labor demand, and therefore we can solve for the wages such that labor markets clear. And the production structure of the model is going to be very rich and built on a previous paper I have with Lorenzo Caliendo, with Esteban Rossi Hansberg, and Pierre Daniel Sarté. And it's going to be relatively standard. So we assume that as in Eaton and Cortum, there is in each labor market, so there is a continuum of intermediate goods producers. Production is with the perfect competition, constant returns to scale, with an idiosyncratic productivity, Z, that's as in Eaton and Cortum, is a draw from a Fréchet distribution with a shape parameter theta, and the theta is going to be interpreted as the trade cost elasticity, and with deterministic sectoral regional TFP A. So this equation shows the production function of goods in labor markets NJ. So it's going to be pretty standard in the sense that to produce goods in industry J and region N, firms demand labor, firms demand structures, which is going to be a fixed factor in this model, and where gamma nj is the share of value added in gross output, okay? And firms also demand materials, M, from all industry, okay, according to input-output linkages. So this is going to be a standard production function with labor, with the structures, and with materials, with intermediate goods, and with input-output linkages. So we're going to have tradable and non-tradable industries. In tradable industries, trade of goods is going to be subject to trade cost. So kappa is the cost of shipping goods from location I to location N in industry J, and it's going to be a standard iceberg trade cost as in the trade literature. And goods within a given labor markets are going to be aggregated using a standard CS aggregator, and therefore we can solve for the price index in the labor market NJ. So this slide is it doesn't have new things. It's more or less standard in the context of recent quantitative trade models. So the first equation describes as the price index in labor market NJ, which is going to depend on X. X is the cost factors in the destination labor market, in the origin labor markets. Kappa are shipping costs, and A are productivities in the origin, the exporting labor markets. We can also solve for the fraction of goods that are purchased by firms in industry J and location N from location I. So this pi describes the gravity trade equation. So this is the gravity trade equation that is delivered by this model. So describe the flow of goods across different labor markets. And at this standard in trade, the numerator depends on the cost of producing goods in the exporting labor market, the trade costs and productivities. So it's a standard bilateral resistant term. The denominator is a standard multilateral resistant term, and theta j is the trade cost elasticity, which also need to be imputed in the model. And the last equation is just the labor market clearing condition. So we have a supply has to be equal to demand, and therefore we can find wages such that labor market clears. So this slide just formalize what I have said so far and defined the equilibrium of this economy. So the state of the economy is given by the distribution of labor across different labor markets, L. And we're going to define as this set theta. So this set theta is going to contain the unobservable fundamentals or parameters in the economy. And it's composed of the productivities in each labor market, bilateral trade cost, bilateral migration cost, the stock of infrastructure in each labor market, and this home production. And therefore, given the distribution of employment at each time t, and given the set of fundamentals of the economy, a temporary equilibrium is going to be a vector of wages that is going to solve the firm problem that I just showed to you. And given the initial distribution of employment, and given the set of fundamentals, a sequential competitive equilibrium of the model is going to be a sequence of employment, a sequence of migration flows, a sequence of values, and a sequence of wages that solve the household dynamic problem, as I first showed to you, and the firm's problem. Okay. Yeah, this is a great question. So in a simplified version of so the question if this equilibrium is unique. So this model can be mapped to a simplified version of this model, so without input-output linkages, where we can show that the equilibrium is unique. So yes, the equilibrium is unique. So this is in terms of the model. What I want to describe now is our solution method, how to take a model with all these ingredients to the data, and how to use the model to perform counterfactual analysis. And after doing so, we are going to go over the application. I'm going to show you our quantification on the impact of China's trade expansion on the US labor markets. So from this slide, so it's pretty evident that solving this model require information on the whole set of unobservable fundamentals, on the whole set theta. And this may be unfeasible in the context of a model with many industries and many regions. So for instance, if you have a model with N regions and J industries, this is the number of unobservable parameters that you need to identify. That includes bilateral migration frictions, bilateral trade costs, productivities, home production, endowment of infrastructure, etc. So just to put an example in the context of our application, where we're going to have 38 countries, 50 US states, and 22 industries, this number is going to be millions. Okay? And of course, as you increase the dimension of the problem by adding countries, regions, or sectors, the numbers of parameters is going to grow geometrically. So how we're going to deal with this issue? So in one sentence, instead of solving the model in levels, okay, we are going to solve the model in relative time differences. And why this is going to be progress? Because by solving the model in relative time differences, we're going to be able to condition on data, and we're going to be able to solve the model without having to identify all these unobservable parameters that are contained in this set theta that I showed you previously. So that is going to be the idea of the solution method. And in the next couple of slides, okay, I'm going to illustrate how the solution method works. And to do so, I'm going to assume that all fundamentals are constant in the economy. And later on, I'm going to deal with the time varying fundamentals. So here you have two of the equilibrium conditions from the household dynamic problem. So remember, the first equation is the value of a household in a labor market Nj at time t. And the second equation is the migration flow equation, okay, that describes the flow of workers across different labor markets. For a moment, first, let's focus on the second equation, the migration flow equation. So from this equation, it's pretty evident that there is an infinite combination of migration cost, tau, and values that can rationalize migration flows in the data. And therefore, in principle, there is no hope that we can estimate or we can compute the values without having any information on migration costs. So, but what we're going to do? So we're going to condition in the first period on the data. So the data here is going to be blue, and mu minus 1 and JIK describes the migration flows in the data at the initial period. And these migration flows in the data is going to contain information on the expected value of going to any labor market at the period 0, and the period 0 times 0 is the first period in the model. Okay, so we are going to take migration flows at the initial period at t minus 1 from the data. We are going to take migration at the period 0, at time equal to 0, from the model, and the migration flows at time equal to 0 is going to reflect the expected value of going to any labor market at period 1, and we're going to take the ratio between both. Okay, so we're going to take the time difference. So mu 0 divided by mu minus 1 where mu minus 1 is taken as given from the data. It's kind of the initial migration flows in the model. So if you look at the numerator, because of the exponential function, so the migration cost, tau, are gonna differentiate out. Okay, so the numerator is gonna depend only on the differences in the values. Still, we have to deal with the migration cost in the denominator. Okay, but we are gonna use again the information contained in the migration flows in the data period at the time -1, and we're going to plug in the denominator the equation that describes migration flows in the data at period -1. And with some algebra manipulation, in the end, we have that migration flows in the model at period 0 depends on migration flows in the data, the initial migration flows in the data, and the differences in the value. And all the migration costs, all the migration frictions are differentiated out. So what you can see in this equation is that the change, the time difference in the value of going to any labor market and the initial migration flows in the data is enough to solve for the entire path of migration flows at each time t. And we don't need information on the, migration frictions. For the case of the value, which is another equilibrium condition from the household dynamic problem, we're going to do the same. So instead of solving for the values in level, we are going to express this value function in time differences. And the logic is the same. In time differences, the value function in time differences, as you can see here, is not going to depend on migration frictions. So migration frictions are going to differentiate out, okay? It's going to depend on the time differences in real wages, and it's going to depend on the migration flows from the previous period. And I already showed how to solve for the migration flows at each time t without having information on migration frictions. And the changes in time, the changes in real wages over time is going to be the solution to the production structure that I showed you some slides ago, expressed in time differences. So here you have two of the equilibrium conditions from the production extractor. So remember the price index and the gravity trade equation that, of course, in levels depends on unobservables such as productivities and trade costs. So again, instead of solving these equations in levels, we are going to express these equilibrium equations in time differences. And in time differences, the price equation in times differences is going to depend on the change in wages, the change in factor prices, and my trade flows from the previous periods. And all the unobservables, productivities and trade costs are going to differentiate out. Same thing for the case of the gravity trade equation. So we're going to express the gravity trade equation in time differences. It's going to depend on the change in factor prices, my trade flows from the initial period, and all the unobservable, such as productivities and the trade costs are gonna differentiate out. So bottom line of this solution methods, so we have this proposition that summarizes what we can do with the solution methods. So it says that given initial allocations from the data, so remember that blue means data, so given the initial distribution of employment, given the initial migration flows, given the initial trade flows, and given the initial allocations of expenditure and production, and given the value of these sort of elasticities, the migration cost elasticity, the trade cost elasticity, and the discount factor, solving the equilibrium of this model in times differences does not require the level of fundamentals. Okay, this is the main result in terms of our solution methods. So it says that to compute the model, okay, we need to condition on initial allocations that are given by the data, and then by solving for the model in time differences, we are not going to need to identify any of the fundamentals, unobservable fundamentals contained in this set theta. Now, I just show you how to compute the model. Now I'm going to describe briefly how to use the model to perform a counterfactual analysis. And after doing so, I'm going to go over the application on the China trade shock. So we want to use the model and we want to use the solution method, our solution method, to study the effects of changes in fundamentals. Okay, so we want to study what are the new equilibrium allocations in the model when there is a change in this set theta. So for instance, the productivities in China, or trade costs, or migration costs, or etc. So in the case of our application, we are gonna study the effects of changes in the manufacturing sectors in China. So what are the new equilibrium allocations? What are the welfare effects in the United States? And to do so, okay, we are going to think about two types of counterfactuals, what we call counterfactual 1 and counterfactual 2. So suppose we want to study, as we are going to do in our application, a change in productivities in the manufacturing sectors in China. So we are going to perform two types of counterfactuals. Both counterfactual are well defined in the sense that I'm going to explain in a moment. Both are going to give us the effect of changes in productivity in China. The difference between a counterfactual 1 and counterfactual 2 is about what we assume about the evolution of the other fundamentals of the economy, other than productivities in China. And in counterfactual 1, we assume that all other fundamentals are going to be constants. And therefore, we are going to solve, in counterfactual 1, we solve for a baseline economy where all fundamentals are constant relative to a counterfactual economy where all the fundamentals are constant except for productivities in China. Okay? And by solving, so remember the solution method, by solving one relative to the other, all the fundamentals that are constant are going to differentiate out, and therefore the only unobservable fundamental that I need to estimate is the one that I am interested in. So the changes in productivity in the manufacturing sectors in China. Okay? In the counterfactual 2, okay, I'm going to allow for other fundamentals other than productivities in China to change over time. So in counterfactual 2, we're going to solve for a baseline economy, okay, that is going to contain the actual evolution of fundamentals, all the fundamentals as in the data. Okay, trade costs, productivities in other countries, everything, all fundamentals are going to evolve as in the data. And we're going to solve this baseline economy relative to a counterfactual economy that is going to contain all the evolution of fundamentals as in the data, except for productivities in China. The productivities in China is going to contain not the actual evolution, but the counterfactual evolution. By doing so, okay, because we are solving in relative time differences, we are able to differentiate out all the fundamentals that evolve in the baseline economy in the same way as in the counterfactual economy, that in the case of this example are all the fundamentals in the set theta except for productivities in China. Okay? So these two counterfactuals have different assumptions about what we assume on how other fundamentals evolve in the economy, but both are going to give us the effect of a change in productivity in China. If you want, counterfactual 1 is answering the question, what is going to be the effect on the United States if nothing happened in the world except for the changes in productivity in China. In the counterfactual 2, the answers the question, what would have happened, what is the effect on US labor markets if all the fundamentals change as in the data, if everything happens in the world as it happens in the world in the data, except for productivity in China. Okay? So, so this is the idea. So this is the type of counterfactuals we are going to solve. I hope if there is any question, but otherwise, I'm going to start with the application. So the application is going to be on the China shop. So just to motivate this topic, probably most of you already know that US import from China almost doubled from 2000 to 2007. And at the same time, manufacturing employment fell in the United States, while employment in other sectors, such as construction and services, grew. So actually, the observed decline in manufacturing employment in the United States over this period is about 3 million, pretty substantial. And this has motivated a lot of recent research to try to determine what fraction of this observed decline in manufacturing employment is due to increased import competition from China. And several studies have documented that an important part of the employment loss in manufacturers was a consequence of China's trade expansion. Okay, and most of these studies, as I mentioned in the introduction, are a reduced form evidence, like Pearson Schott and Otterton and Hans. So what we want to do next is we want to use our general equilibrium model with all these mechanisms or all these ingredients I have described, and we want to apply our solution method to quantify and understand the effects of the rise of China's trade expansion, which is called for us and in the literature the China shock. So our initial period is going to be the year 2000, and we are going to compute many results. Since we have this machinery, this general equilibrium model, we can compute many outcomes that we are interested in. So we are going, for instance, we are going to compute the sectoral, the regional, and aggregate employment effects and the welfare effects of, crucially, because we have a general equilibrium model, we are going to compute the welfare effects of the China shock. So remember from the solution method, okay, that and for the counterfactual slide, that to compute the effect of the China shock, we don't need to identify the unobservable fundamentals of the economy, except for one, right, which is the change in productivities in China, the China shock, and that is what I'm going to show you next. How we identify, so that before computing the results, we need to identify the China shock. And to identify the shock, okay, to identify the shock, we're going to use reduced form analysis. And actually, we are going to follow the same identification strategy as Otterton and Hanson. And the basic idea is the following. So I already told you that we observe that the imports, the US import from China more than double from 2000 to 2007. But of course, part of this increase in US imports from China can be not due to China, can be endogenous to the United States. So Otterton and Hanson instrument the observed change in US import from China to get the fraction of the change that is due to China. And the instrument they use is the imports by other advanced economies from China. So using as an instrument the imports by other advanced economies from China, they obtain the predicted change in US import from China that can be attributed to China. And in Otterton and Hanson, that is the China shock. Okay? In the case of our model, we are going to follow exactly the same identification strategy, but with the additional step that imports in our model are endogenous. Okay? So we are going to find the changes in productivity in China in the 12 manufacturing sectors that we have that predict exactly the predicted change in the US import from China using the instrument of Otterton and Hanson. Okay? I don't know if there is any question on this. Otherwise, I can continue. So, just to recap, the changes in productivities in China. Oh, thank you, Alberto. So it's very difficult to know if people, you cannot see faces. So just to recap, the changes in productivity in China that match exactly the predicted change in US import from China using the instrument of Otterton and Hanson is our China shock. And this is the shock that we are going to fit into our general equilibrium model. So after identifying the China shock, we need to calibrate the model. So we are going to calibrate the model to 50 US states, 22 sectors. So as I mentioned, 12 manufacturing sectors, 10 non-manufacturing sectors. There is going to be an additional sector that is going to be called non-employment. Okay, remember that in the model, households can choose to go to a non-employment sector in each period, and we're going to have 37 other countries and China. Okay, so again, we're going to have a model with 50 US states, 22 sectors, and 38 countries. Trade is going to be across US states and across countries. Migration flows is going to be only across US states. So we are not going to allow for international migration, okay? And that is a constraint in the data. So we don't have gross migration flows across countries. But we're going to have trade across US states and across countries, okay? But migration flow is only going to be about internally in the United States, across different industries and different regions. So for the case of the United States, since we have 50 US states and 22 sectors, and a labor market is a combination of a sector and a US state, as I said, for instance, computers and electronics in California, we're going to have more than 1,000 labor markets. So to compute the model, as I explained in the solution method, we already identified the China shock. Now we need to compute from the data the initial allocations. So the initial distribution of employment, initial migration flows, initial trade flows, and initial value added and expenditure allocations for the year 2000, which is our initial year. So I'm not going to stay here too long, but in the paper we have a lot of details on how we construct all these initial allocations. All the data sources are ready available and are pretty standard. So the initial distribution of employment is from the US Census. The initial migration flows combine data from the CPS and the American Community Survey. Trade flows, internal trade flows across US regions comes from the Commodity Flow Survey. International trade flows comes from the World Input-Output database. And production data, gross value, value added, for different industries and regions in the United States come from the Bureau of Economic Analysis. And for other countries, we obtain this production data and the parameters of the production function from the World Input-Output database. So a lot of data, several different sources, but all the data needed to compute the model is ready available in well-known databases. So remember the solution methods. So we need to identify the China shock. We need to compute the initial allocations from the data, and we need to input a value for these three elasticities, the migration cost elasticity, the trade cost elasticity, and the discount factor. Okay, so the trade cost elasticity is obtained across industries from Caliendo and Parro. It's a previous paper I have with Lorenzo on NAFTA, where we develop a method to compute these trade cost elasticities. That method is consistent with any model that delivers a gravity trade equation and therefore is consistent with the model I am presenting today. So our model is going to be quarterly. We are going to choose a discount factor of 0.999. So the migration cost elasticity, we need to estimate a quarterly migration cost elasticity. We compute this elasticity using the methodology of Artuk, Chadguri, and McLaren AER paper. So we don't innovate on a new methodology to estimate this migration cost elasticity, but we make the estimation consistent with our model, the estimating equation consistent with our model, and consistency with our frequency. And we obtain a value of 5.34. In the model will also deal with endogenous trade deficits across countries and within the United States across regions. So in the data, of course, you see that trade deficits are huge. And so for any reasonable, credible quantification, we need to deal with the endogenous trade deficit. We do it like in a very simple way that is borrowed from a previous paper with Lorenzo Caliendo, Esteban Rossi Hansberg, and Pierre Daniel Sarté. And just to give you an idea, okay, what we do, we assume that all the revenues from the infrastructure for the structure, which is again a fixed factor in the model, are transferred to a global portfolio, and each labor market has a constant share of this global portfolio. And that means that the differences between the remittances to the global portfolio and the transfer income from the global portfolio are going to create imbalances. And this constant share of the global portfolio is going to be disciplined to match observe trade deficits. So a very simple way, but it's borrowed from a previous paper. And what I always emphasize here is that it makes progress with respect to traditional trade literature to try to capture endogenous trade deficit, because until recent years in trade, we usually assume that trade deficits do not exist, or they are constant over time. Okay, so we already identified the China shock. We already compute the initial allocations. We already input values for these three sort of elasticities. What we are going to do next is to proceed to do the counterfactual analysis. So we're going to feed into our calibrated model the changes in productivities across Chinese manufacturing sectors, and we are going to see what are the labor market outcomes and the welfare effects in the United States. Sorry. So first, I'm going to show you the employment effects. So these figures shows the evolution of the employment shares for the manufacturing sector as an aggregate, for the services sector, for the construction sector, and for the wholesale and retail. So let's focus on the one that has been the focus in recent literature, and manufacturing first. So these are the results for the case of constant fundamentals, and therefore, okay, the dashed blue line shows the evolution of the manufacturing employment share with the constant fundamentals. Okay, so why we have transitional dynamics even when we have constant fundamentals in that simulation? Because remember that at the initial year, So we calibrate the model using the initial allocations computed from the data. And therefore, at the initial year, our model is just a perfect representation of the world. So it's a picture of the economy, and an economy that is not necessarily in a steady state in the year 2000. So different from, if you want, a kind of a traditional macro literature, because the way in which we solve the model using observed data for the initial allocations, we don't need to assume that the model is in a steady state, and it's very likely that the economy is not in a steady state in a given year. And for that reason, you can see with the dashed blue line that you still can see transitional dynamics even when we assume constant fundamentals. So the green line shows the evolution of the manufacturing employment share with the China shock. When we fit into the model, the changes in productivity across manufacturing sectors in China. And therefore, the difference between the green and the blue dashed line is the change in manufacturing employment shares that we attribute to the China shock. Okay? And in terms of the numbers, we find that increased import competition from China reduced the share of manufacturing employment by about 0.5% in the long run, which is equivalent to about 800,000 manufacturing employment jobs lost, which is also equivalent to about 25% of the observed decline in manufacturing employment over the period 2000 and 2007. Yeah, so that is a great question. So the model would be too complex to solve. No. So in this paper, we want to focus on, we want to make progress on introducing other channels that are, we think that are first order, such as, and that has been absent in previous literature, such as the labor market dynamics, together with all the details in the production of structure of the economy. Introducing capital accumulation is feasible to do. It's an open question how much mattered for our results. We don't know. It's an interesting avenue of future research, and actually we are thinking about that right now for a new paper. Yeah, absolutely. So I'm going to show you the effect on real wages across different labor markets in a second. Okay, absolutely. So the wages are endogenous, are an outcome from our model, and of course, I mean we can compute, we can show the evolution of wages. Yes. So, any other question? Okay, you're welcome. So then, going back to the figure, we find kind of 800,000 decline in manufacturing employment. If you look at the other figures, and let me fix this. If you look at other figures, we find that workers, so the employment in services sectors grew, the employment in the construction sector grew. And so because the services sector expanded as a consequence of the China shock. And it is crucial, kind of the input-output linkages, to understand this, because the services sector is a sector that has no direct exposure to China. Because think about non-tradable sectors. So they have no direct exposure to China, but they use materials from the manufacturing sector to produce. And therefore, with the China shock, now the services sector has access to cheaper materials from China, and that allows to expand production and to absorb the employment displaced from the manufacturing sector. Okay, we also see an increase in employment in the construction sector. I think that we have the number in the paper about 75,000. Okay. Since we have a general equilibrium model, we can speak much more about employment effects. So here I'm just going to mention a couple of results. So unfortunately, I think that I cannot go to the hyperlinks, but first we compute which manufacturing sectors explain this decline in manufacturing employment. And we find that the computers and electronics sector and the furniture sector explain about half of the total decline in manufacturing employment, the aggregate decline in manufacturing employment. Why? So the intuition is more or less straightforward because these are sectors with a high exposure to China. Other sectors are also important. Textiles and metals explain about 25%, 1/4 of the total decline in manufacturing employment. We have some sectors that gain in employment. For instance, food, beverage, and tobacco. Again, why? Because food, beverage, and tobacco is an industry that with little exposure to China, but uses a lot of materials from other manufacturing industries to produce, and therefore this industry benefited from cheaper intermediate goods from other sectors such as services and such as other manufacturing industries, which allow this sector to expand production and increase employment. Then we do the same about regions. Okay, we want to quantify which regions contribute more to this decline, to this aggregate decline in manufacturing employment. Okay, and we find that California explained about 12% of the aggregate decline in manufacturing employment, and is the largest contributor in the United States to the decline in the manufacturing employment as a consequence of the China shock. So what is the intuition? So California so remember that computers and electronics is a sector with a very high exposure to China, and most of the production, most of the employment in computers and electronics is concentrated in California. So California concentrates about 20% of the aggregate total US employment in computers and electronics. The second state is Texas with 8% of the total employment in computers and electronics, and all other regions are below 2% or so. Okay, so in the paper, again, unfortunately here I cannot use the hyperlinks, but in the papers also we compute what happens in the non-manufacturing sectors. Sorry. So here we have the welfare effects. This is a histogram that shows the welfare effects measured in terms of consumption equivalent. So this is not exactly you were asking, Alberto, because the welfare effects contains, as I said previously, two components: changes in real wages and also the change in the option value of migration. But this, you can take this as an indication of what happened with the real wages across different labor markets. And so a couple of interesting results here. So at the aggregate level, we find the welfare in the United States as a whole increased by about 0.3% as a consequence of the China shock. Welfare gains. A lot of heterogeneity. And some labor markets experienced welfare losses as a consequence of the China shock. So some other labor markets experience large welfare gains. So overall, again, who are the largest winners from the China shock? Labor markets that produce services. Again, what is the intuition? Services are sectors, are non-tradable sectors that have little exposure to China, but benefits substantially from the access to cheaper intermediate goods from China as a consequence of the increase in productivity in China. Who are the largest losers? Labor markets that are very isolated, labor markets that are very intensive in industries that have a high exposure to China. Here we compute the transition cost. So the transition cost, the meaning of the transition cost is how much welfare is lost across labor markets because the economy does not jump immediately to a steady state. In the context of previous static or previous trade models with completely free labor mobility, this histogram would have been empty. So yes, Francisco, can you derive policy implication from your model to mitigate the cost? Yeah. So I don't have this in the presentation, but in the paper we have a section where we study what are the effects in the economy if there is an increase in the generosity of the disability insurance to try to smooth the negative adverse effects of the China shock. Yeah. So regarding the second part of your question, yes, we have this effect in the model. So mainly the welfare gains at the aggregate level are explained because of a decline in the price index, because the economy as a whole had more access to cheaper goods from China, and the price index in the economy decline as a result. So we have that in our welfare calculation. The first one, yes, the first one is a great question. Is part of our research agenda. I mean, how to study sort of what you said, the compensation and transfer across different sectors. So that everyone could be better off. That is a great question. We started thinking about that, and it's part of our research agenda, but it's not part of this paper. So, so going back to the figure, so these transition costs are positive on average, heterogeneous across labor market, and shows that adjustment of the economy, reallocation, takes time. Okay, And that is another policy implication that we don't address here, so related to Alberto's question, but is very interesting to study. So what type of policy could help move faster workers displaced from the manufacturing sector? So what type of policy could help the losers of the China shock? So workers that are displaced from the manufacturing sector that cannot insert immediately in a different industry. So those are all, great questions to study in the future. So finally, we compute the welfare effects across the rest of the countries in our sample. So we find heterogeneous welfare effects. We find that all the rest of the world is better off as a consequence of the China shock, and the main reason is again because the increase in productivity in China allow all countries have access to cheaper goods, and because of the decline in the price index, we find positive welfare effects from increased trade with China. And just to conclude, so in this paper, we develop a dynamic and spatial model to quantify the disaggregate effects of aggregate or trade shocks. This paper has kind of two contributions. So the first one is the methodology, which is kind of we believe a step forward in the literature to show how to perform counterfactual analysis and how to solve a model which is a large scale and has a lot of mechanisms that previous literature have shown to be relevant in terms of the number of industry, number of sectors, trading goods, input-output linkages, labor market dynamics, migration restrictions, and so on. We find that this realistic structure matter for capturing in the right way the aggregate and disaggregate effects of increasing import competition. And what we want to emphasize is that in this paper we applied our solution method and our model to study the effect of the China shock, which is of course a first order question. But the model can be applied to answer a much broader set of questions, changes in productivity or trade costs in any location in the world, commercial policies, and more. So actually, in a recent paper, we have applied the same machinery to study the consequences of the 2004 European Union enlargement, when 10 new member states joined the European Union. As a consequence, there was a change in trade policy and there was a change in migration policy. So in that paper, we studied the effect of changes in this Tao as a consequence of changes in migration policy. So we believe a super important question, and the machinery that we have developed in this paper is very well suited to answer those type
of questions. Fernando, thank you very much. It was very interesting. So let's wait a couple of seconds to see if there are any other questions, and otherwise we conclude the seminar. So I don't see anyone typing. So thank you, Fernando. Very interesting again, and thank you everyone for joining our webinar series.